This image captures professional pushers at a Tokyo train station. Their entire job involves forcefully packing commuters into overflowing railcars. When a city runs out of space, the cost of whatever real estate remains available skyrockets. In global hubs like Paris or London, even those earning top salaries struggle to afford housing, often relegated to fractional square footage they cannot realistically own. For billions of others, the density problem creates a humanitarian crisis. This photograph shows Dharavi in Mumbai, where a lack of viable housing forces hundreds of thousands of people into a single square kilometer of substandard conditions. This chart tracks the United Nations official projections for urban growth. Over the next 25 years, we expect to add another 2.5 billion people to our cities, pushing the global urban population past the 70. We have a strictly limited surface area and are quite literally running out of horizontal ground to put people on. To absorb the incoming population, our cities need a new dimension. This is Zocalo Square, the heart of Mexico City. It is a 240 by 240 meter open space, sitting in the center of one of the most intensely crowded metropolises on Earth. You can see ancient Aztec ruins preserved right next to modern structures in this photograph. Because of these buried heritage sites, strict local laws cap new construction in this area to a maximum of 8 stories, making vertical expansion impossible. In 2011, the firm BNKR Arquitectura looked at that absolute limit on upward growth and proposed going in the opposite direction. This diagram illustrates their proposal, the Earthscraper. It is a 65-story inverted pyramid plunging 300 meters directly beneath the square, hollowed out in the center by a massive light well. The layout isolates different civic functions by depth. The first 10 floors are dedicated to museums and cultural centers, designed to display the Aztec artifacts found on site. The lower sections provide space for dense residential and commercial real estate. While a 65-story underground city looks like science fiction, the raw engineering suggests that building a deep subterranean tower is within our current physical capabilities. Humanity survived in massive underground networks before. This photograph shows the interior of Derinkuyu in Turkey, an ancient underground city extending 18 stories below the surface. It was built to house 20,000 people, complete with complex ventilation shafts. Modern equivalents exist right now. Beneath Helsinki, Finland, a massive 293-kilometer underground network houses vital civic infrastructure and emergency reserves, and even features massive sports facilities up to 15 floors deep. And this photograph shows the GCANS project in Tokyo. It is a massive subterranean flood reservoir buried 50 meters underground, supported by 500-ton concrete pillars. Combining ancient human adaptability with our current ability to execute megaprojects proves the Earthscraper is technically within our reach. Lateral earth pressure will quickly collapse a 300-meter void. To counter it, engineers secure the perimeter with 2-meter-thick diaphragm walls. Next, slanted vertical support columns form a deep bedrock skeleton. Finally, they excavate the center, pouring concrete floors layer by layer to lock the structure. This photograph captures the aftermath of seismic activity in central Mexico. The primary concern for an earthscraper in Mexico City is surviving a major earthquake. This animation illustrates how seismic resonance affects different structures. While a tall skyscraper is whipped back and forth by ground displacement, an underground structure moves uniformly with the surrounding soil, minimizing destructive resonance. To eliminate the darkness, massive bundles of fiber optic cables surround the light well, gathering surface sunlight and transmitting it to diffusers placed on the deepest floors. To successfully handle the sudden threats of subterranean flooding or fires, the underground design relies on heavy industrial pumping systems and dedicated water reserves already used in modern subway networks. Every environmental threat thrown at the Earthscraper has a calculable technological countermeasure ready to be deployed. The math works, the precedents exist, and the engineering is viable. Yet the Earthscraper has sat completely paralyzed as a mere concept since 2011. The first massive roadblock is political. Zocalo Square is intensely sentimental to the Mexican public. Accidentally destroying undiscovered Aztec antiquities with a drilling rig would cause immediate societal outrage. Then there is the financial risk. This project carries an estimated price tag north of $800 million. Recouping that cost requires selling high-end residential leases, but developers have no data to prove buyers will pay a premium to live hundreds of meters underground. Finally, government regulators would have to create entirely new protocols for fire evacuation, radon gas monitoring, and structural audits, a process that could freeze construction in bureaucratic limbo for decades. The Earthscraper remains stalled because our collective aversion to financial and political risk currently outweighs the undeniable logic of the engineering. We have a long history of rejecting major technological leaps out of a desire to protect the status quo. Western Union dismissed the telephone as a toy with too many limitations. Early corporate executives couldn't fathom why an ordinary citizen would ever want a computer inside their house. A true innovation always looks foolish, expensive, and dangerous, right up until the exact moment sheer necessity shatters the status quo. Solving the global housing crisis requires the collective courage to look past standard construction and rethink the actual geometry of human space.